Today, we're breaking down the science that powers pretty much everything in our modern world, electronics. We're going to peel back the cover and take a look at the fundamental magic that makes your phone, your car, well, everything, tick.
It seems like a simple question, but really think about it for a second. Yeah, they both use electricity, but how they use it is worlds apart. A toaster just gets hot. A smartphone, it processes information, and that single difference, making heat versus processing information, that's the key to understanding all of this.
Okay, so let's get right to it. We need to understand the crucial difference between two words we kind of throw around interchangeably, electrical and electronic. They sound similar, but as you're about to see, they are fundamentally different things. So here's the breakdown. Electrical systems, they're all about raw power. Think high-voltage AC current doing big physical jobs. But electronic systems, they're all about intelligent control. They use low-voltage DC current to precisely manipulate the flow of electrons, and that's how they process signals.
So if you remember one thing, it's this. Electrical systems just convert energy to do a physical task. Think power. Electronic systems, on the other hand, intelligently regulate that energy to do sophisticated things, to basically make decisions. Think control and signals. Now, how is this kind of intricate control even possible? I mean, how can we manipulate energy with that much precision? Well, it all comes down to the fundamental properties of the materials we choose to use. Okay, so let's get down to the quantum level. Every material has two, let's call them lanes for its electrons. There's a home lane where they stay put, and then there's a free flow lane where they can move around and create a current. For electricity to flow, an electron has to jump from its home lane to that free flow lane, and the size of the gap between those two lanes, well, that changes everything. So in conductors, like the copper in our wires, the home lane and the free flow lane completely overlap. There's no gap at all. That means electrons can just cruise around with incredible ease. It's basically an open highway for electricity, which is exactly why we use it.
Now, on the complete opposite end of the spectrum, you've got insulators, things like rubber or plastic. Here, that forbidden gap is enormous. It takes a huge amount of energy for an electron to even think about making that jump. So much energy, in fact, that it just doesn't happen. The current is stopped dead in its tracks. And this brings us to the hero of our story, the semiconductor. Materials like silicon have this small, totally manageable energy gap. It's not zero, but it's not massive either. It means electrons can be persuaded to make the jump. And that little gap right there is the secret ingredient to all of modern electronics.
I mean, just look at this chart. The difference in resistance is staggering. An insulator can have a resistance trillions upon trillions of times higher than a conductor. And sitting right there, perfectly positioned in that massive gulf between them, you find the semiconductors.
So how do we harness this unique, middle-of-the-road property? How do we take a material that's just kinda conductive and turn it into the absolute foundation of all computing?
And here it is. This is the breakthrough. A copper wire is always on. It's always a conductor. An insulator is always off. But a semiconductor can be told when to conduct, how much to conduct, or when it should just act like an insulator. This is what makes control possible.
Scientists pull this off through an amazing process called doping. It sounds weird, but it's really just intentionally adding tiny amounts of impurity atoms into an otherwise ultra-pure crystal of silicon. It's kind of like adding just a tiny pinch of salt to a recipe and completely changing its flavor.
So, by doping in two different ways, we can create two different types of materials. N-type doping gives the silicon extra free-moving electrons that gives us a negative charge carrier. Then there's P-type doping, which creates holes, these little spots where an electron should be, and these holes actually move through the material just like a positive charge would.
So what can you build when you strategically combine these two new types of materials? Well, you can build the single most important invention of the 20th century, the device that underpins our entire digital world.
It's called the transistor. By creating a sort of sandwich of N-type and P-type materials, we can make a device that acts like a tiny solid-state switch with absolutely no moving parts. A small electrical signal can turn a much larger flow of current on or off.
And that simple on-off function, that is everything. That function is what allows transistors to speak the binary language of computers. Every single 1 and 0 that makes up your photos, your apps, this very explainer, it's all just a transistor somewhere that's either switched on or switched off.
But the real power, the real magic comes from the scale. we're not talking about a handful of switches that you can see. We are talking about billions of them, miniaturized and packed onto a single silicon chip smaller than your fingernail.
Billions. That's how many transistors are on a modern processor, and every single one is capable of switching states millions or even billions of times per second. It's this coordinated, lightning-fast dance of billions of tiny switches that allows our devices to do what they do.
Okay, let's zoom back out for a second. We've gone from the basic difference between power and information all the way down to the atomic level, and then back up to the invention of the transistor. Now let's just see how these billions of tiny switches have built the world around us.
Just think about your daily life. The smartphone in your pocket, the complex control systems in your car, the critical medical instruments in a hospital. Every single one of them relies on these integrated circuits packed with transistors made from doped semiconductors.
And so here we are, full circle. This is the answer to that question from the beginning. The toaster? It just converts electrical energy into heat. Simple. But the smartphone, the tablet, the computer, they intelligently manipulate that flow of electricity to manage information. And that is the power of electronics.
It really is a powerful thought, isn't it? The ability to control the flow of electrons, scaled up billions and billions of times over, has already completely reshaped our world. And as we get better and better at making and arranging these tiny switches, the question isn't just about what they can do now, but what they'll enable us to do next.